In this video, we will practice our function transformations. This is AP Precalculus Topic 1.12. If you appreciate this content, please don't forget to hit that like button. Number 1, let g be a function that is a transformation of function f, such that g of x equals 1/2 f at x plus 2 plus 5. Describe the transformations of the function f that result with function g. Changes that appear inside of the function are horizontal transformations. So this plus 2 is going to be a horizontal something. When you are adding or subtracting, that is going to give you a translation, like a slide. Horizontal transformations are always the opposite of the way they look in the function. So f of x is translated horizontally -2 units, not +2. Changes that occur outside the function are vertical transformations, and they happen just like they look. So this multiplying by 1/2 in the front is a vertical dilation by a factor of 1/2. And the plus 5 on the end means that f of x is translated vertically by 5 units. Number 2, let k be a function that is a transformation of function h, such that k of x equals 4 times h at x over 3 minus 1. Describe the transformations of the function h that result with the function k. I like to do a little bit of a rewrite here for clarity. Sometimes students see this part and think 4h, but that's wrong. This is 4 times the function h at x over 3. I also like to rewrite x over 3 as 1/3 x, so you can more easily see this horizontal transformation. Let's go ahead and talk about that 1/3. Multiplying by something is going to be a dilation. Any change happening on the inside of a function is a horizontal transformation. So h of x is dilated horizontally. Now, these changes on the inside of the function always occur in the opposite way from the way they look. So it will be a horizontal dilation by a factor of 3 instead of 1/3. Think reciprocal. 4 is multiplying, so that's going to be another dilation, but this time it is outside the function, so this will be a vertical dilation, and it will happen exactly the way it looks. h of x is dilated vertically by a factor of 4. Now this -1, when you are adding or subtracting, that is a translation of some sort. Since the -1 is outside the function, this is going to be a vertical transformation. h of x is translated vertically by -1. In other words, h of x is shifted down 1. Number 3, let r be a function that is a transformation of the function p such that r of x is equal to -3 times p at 4x. Describe the transformations of the function p that result with the function r. Let's start with the 4. When you multiply, that's going to be a dilation, and changes that happen on the inside of the function are horizontal transformations. Also, horizontal translations occur in the opposite way from what appears in the function. So instead of a 4, you get a 1/4. p of x is dilated horizontally by a factor of 1/4. Now let's talk about the 3, without the negative sign. The negative sign is its own transformation. When you multiply, that is a dilation. Since this is occurring outside of the function, it will be a vertical dilation. p of x is dilated vertically by a factor of 3. A negative sign in front means some type of a reflection. Since this is outside of the function, this will be a vertical reflection. In other words, a reflection over the x-axis. So those are the 3 transformations of the function p that we see. Number 4, let n be a function that is a transformation of the function m, such that n of x equals 5 minus m at -x. Describe the transformations of the function m that result with function n. I think it will be easier to interpret if we move this 5 to the end. and it becomes a plus 5. Now let's work from the inside out. A negative on the inside of the function is a reflection over the y-axis. So m of x is reflected over the y-axis. M of x is also reflected over the x-axis because of the negative in the very front. Finally, a plus 5 on the outside of the function means m of x is translated vertically by 5, which means a shift up 5. The table below gives values for a function f at selected values of x. Use the table to answer 5 through 6. Number 5. Let g of x equal 2 times the function f at x over 2 minus 3. Find the following values. Finding g at negative 10 means plugging negative 10 in for x. So this is going to become 2 times f at x divided by 2. So that's negative 10 divided by 2. I'm going to go ahead and put in my negative 5. And then minus 3. So what is f at negative 5? Well, here's negative 5, and here is f at negative 5. So this is going to become 2 times 2, and then minus 3. So we get 4 minus 3, which equals 1. Part B, g at 0. Let's plug in 0 for x right here. So we get 2 times f at, and 0 divided by 2 is just 0, and then minus 3. So this is going to become 2 times, now what is f at 0? Here's 0, f at 0 is 6. So 2 times 6 minus 3. So this is 12 minus 3, which is equal to 9. For number 6, let h of x equal 4 minus f at x minus 2. For part A, we need to find h at 2. So we will substitute 2 for x right here. So that's going to give us 4 minus f at 2 minus 2. That's f at 0. What is f at 0? There's 0. F at 0 is 6. And 4 minus 6 is negative 2. So that's the answer for part A. For part B, we are substituting 4 in for x. So that's 4 minus 2, which is 2. So we have 4 minus f at 2. Here's 2, so f at 2 is negative 4. So that's 4 minus negative 4. We know that this is the same as 4 plus 4, so the answer is 8. Number 7. The function k is constructed by applying 3 transformations to the graph of h in this order: a horizontal dilation by a factor of 4, a vertical dilation by a factor of 1/2, and a vertical translation by 3 units. If k of x equals a times h at bx plus c, find the values of a, b, and c. A horizontal dilation by a factor of 4 is going to appear as a multiplier on the inside of the function. But any horizontal transformation appears the opposite of what it is. So instead of a 4, we will have a 1/4. And then we have a vertical dilation by a factor of 1/2. A vertical dilation will be a multiplication out in the front, and it will appear exactly the way it looks. So we will have a 1/2 out in the front. And finally, there is a vertical translation by 3 units. Vertical translations happen on the end of the function, and they happen just like they look. So this will be a plus 3. So a is 1/2, b is 1/4, and c is 3. Number 8. The function h is constructed by applying 3 transformations to the graph of f in this order: a horizontal dilation by a factor of 1/2, a vertical dilation by a factor of 5, a vertical translation by -7 units. If h of x is equal to a times f at bx plus c, find the values of a, b, and c. First, the horizontal dilation by a factor of 1/2. Horizontal stuff appears on the inside of the function. It will be the opposite of the way it looks. So horizontal dilation by a factor of 1/2 will appear as a 2x. Then we have a vertical dilation by a factor of 5. That appears in the front, and it looks just like it says, 5 times f of 2x. And finally, a vertical translation by -7 units appears on the end, and it appears just like this, so -7 on the end. So a is 5, b is 2, and c is -7. Number 9. The function k is constructed by applying 3 transformations to the graph of m in this order: a horizontal dilation by a factor of 3, a vertical dilation by a factor of 1/4, and a vertical translation by 8 units. If k of x is equal to a times m at bx plus c, find the values of a, b, and c. Let's see a horizontal dilation by a factor of 3. That's going to appear right here, but the horizontal transformations show up as the opposite of the way they sound. So by a factor of 3 will actually be a 1/3 in this equation. And then we have a vertical dilation by a factor of 1/4. Those show up in the fourth, and they look like they sound, so 1/4. And finally, a vertical translation by 8 units. That goes on the end, and it looks like it sounds, so +8. So a is 1/4, b is 1/3, and c is 8. Number 10. The function p is constructed by applying 3 transformations to the graph of g in this order: a vertical dilation by a factor of 2, a reflection over the x-axis, and a horizontal translation by 4 units. If p of x is a times g at x plus c, find the values of a and c. A vertical dilation by a factor of 2 will show up as a 2 in the front. However, a reflection over the x-axis is a vertical reflection, so that's going to show up in the front as well as a negative sign. So really we have a -2. And then a horizontal translation by 4 units is going to show up as an addition or a subtraction on the inside. Because these horizontal translations always show up as the opposite of what they appear, then we will have x minus 4 instead of the +4 that we see. So a is -2 and c is -4. Number 11. The graph of y equals f of x, consisting of 2 line segments and a semicircle, is shown on the closed interval from -4 to 3. Sketch a graph of g on the same axes above, where g of x is equal to f at x minus 2. We have one transformation happening to f. Because of the -2, f of x is horizontally translated by 2 units. That's right 2 because horizontal transformations are always the opposite of the way they look in the equation. So I just need to take all of my key points and shift them to the right by 2. So this dot, this endpoint, will end up here. This little cusp will end up here. Okay, this corner, okay, where the semicircle begins, will end up here. The bottom of this semicircle will end up here. And this endpoint will end up here. Our translated sketch will look something like this. We should label it g of x. Number 12. Here's the graph of f, and we are being asked to sketch h of x, which equals 2 times f at x plus 1. Once I see that we have some dilations happening, I like to just go ahead and make a table of values to keep track of what's going on. So I will list off the key points that we see. The first one is the endpoint at -4, 1. And then this corner here at -2, 1. The bottom of the semicircle is at 0, -1. And this pointy cusp right here is at 2, 1. And the final endpoint is at 3, -3. Changes that you see inside the parentheses are happening to the x values, but they are the opposite of what they appear. So I can find new x values by doing x minus 1. Changes that you see outside the function are happening to the y values, and they are happening exactly as they appear. So I can find new y values by doing 2 times y. Subtracting 1 from all the x values gives us this, and multiplying all the y values by 2 gives us this. So all we have to do is plot these points one by one. So the point that originally was here at -4, 1 will now be at -5, 2. So that point is going to be here. This is the new endpoint. This corner, which used to be at -2, 1, is now at -3, 2. So that's going to be right here. And next, the bottom of the semicircle, which was at 0, -1, is now at -1, -2. So -1, -2. Okay, that's way down here. This cusp, which used to be at 2, 1, is now at 1, 2. So that's going to be right here. And the final endpoint, which was at 3, -3, is now at 2, -6. So our new graph h of x will look something like this. Don't forget to label it. We were expecting a horizontal translation of -1, in other words, a shift 1 to the left, and we do observe that. Because of the 2, we were looking for a vertical dilation by a factor of 2. And you can see how this is stretched out twice as tall as it was before. Number 13 is the same type of problem, but our new function k of x is -2 times f of x plus 1. So all of the transformations that I see are happening outside the function. So these will all be affecting the y values. So the x values won't actually change. So vertical transformations occur exactly the way they look in the equation. So to find new y values, I can just do -2 times y plus 1. Let's walk through a couple of them together. -2 times 1 is -2, but then plus 1 is -1. And I see 3 of those actually, so that's going to be -1 for all of them. Now, -2 times -1 is +2, plus 1 will be 3. And finally, -2 times -3 is +6, plus 1 is 7. So I am plotting my original x values and my new y values. So we have -4, -1, -2, -1, 0, 3, 2, -1, and 3, 7. Alright, this is going to be off the graph. So k of x will look something like this. See if you can observe the reflection over the x-axis that we were expecting, a vertical stretch, well, we should say a vertical dilation by a factor of 2, which we can see, and a little bit harder to see, but a vertical translation of +1, so up 1 after the other two things. We can see it. Number 14 only has one transformation. The negative sign right here is a reflection over the y-axis. So most of you can probably just do this visually without a chart, in which case you would be doing things like, okay, this point right here, I see it is 4 units to the left. If I reflect that over the y-axis, it's going to end up right here. And you can just do that one by one. So like this endpoint over here, I see it as 3 units to the right. It's going to end up over here 3 units to the left. But you could use a table. So this transformation on the inside is only going to affect x values. So the y values will not change. The x values will simply be the opposite of whatever they were. So this will become 4 and 2. This stays 0, -2, -3. So we could just plot these points if you like to use a chart instead of just sort of eyeballing it. So we would get 4, 1, which is what we saw right here, and we would have 2, 1, which would be right here, 0, -1, which is still right here, -2, 1 would be right here, and -3, -3, and that's what we have right here. So P of x would look like this. Number 15, looks like we have one more of these. The only transformation is a horizontal dilation by a factor of 1/2, the opposite of what it appears. So I can find new x values by doing 1/2 x. So this will be -2, -1, 0, 1, and 1.5. So plotting these points, we have -2, 1. So that's going to be right here. All right, that's my new endpoint. -1, 1. 0, -1 is still in the same spot. 1, 1 is going to be right here, and 1.5, -3. So over 1.5 and down 3. So m of x will look something like this, and we can easily see the horizontal dilation by a factor of 1/2. Number 16, the domain of a function h is -4 is less than or equal to x, which is less than or equal to 7. And the range of h is -6 is less than or equal to y, which is less than or equal to 0. Find the domain and range of g, where g of x is 3 times h at x minus 2. I like to use tables for this. The domain is the set of x values of a function, and the original endpoints of these x values are from -4 to 7. So looking at the transformations that affect x value, I observe this x minus 2, which is a horizontal translation of 2 units. That's 2 units to the right. So I can find the new domain endpoints by doing x plus 2, the opposite of what we see. So if I do -4 plus 2, that's -2. And if I do 7 plus 2, that is 9. So these will be the new endpoints of my domain. Similarly, the range is the set of y values of a function. And here are the initial y value endpoints of my range. And they are from -6 to 0. What transformations will affect the y values? Well, I just see the 3 that's outside the function. This is a vertical dilation by a factor of 3, so I can find new y values using the expression 3 times y. 3 times -6 is -18, and 3 times 0 is 0. So the range of g is -18 is less than or equal to y, which is less than or equal to 0. Number 17, here's the domain and range of the original function k. Find the domain and range of r, where r of x is -2 times k at 2x. Domain is the x values, the range is the y values. So here are the original x value endpoints, and these are the original y value endpoints. So for the new x value endpoints, the new domain, we need to look at the transformations that affect the x values. I see the 2 multiplying the x. This is going to be a horizontal dilation by a factor of 1/2, because all of the horizontal transformations are the opposite of the way they look in the equation. So I can find the new endpoints of the domain by multiplying the old endpoints by 1/2. So that's going to be 1 and 7. So here is the domain of R. For the range, we are looking for transformations that affect the y values. I see this -2 out in the front, so I can find new y values by doing -2 times y. That'll be 6 and -4. So the range of R will look like this. Make sure you are putting these in order from least to greatest. One more, number 18. Here is the domain of function f, and here's the range of function f. Find the domain and range of function p, where p of x equals 5 minus 3 times f at 2 times x plus 1. I think p of x will be easier to interpret if we move this 5 to the end. So p of x really is like this with a plus 5 on the end. So the domain is the x values, and the original endpoints of the x values are -6 and 4. To find the new domain, I need to consider the transformations that will affect these x values. Transformations that affect the x values appear as changes on the inside of the function, and I see 2 of them. The 2 right here is going to give us a horizontal dilation by a factor of 1/2. Alright, the horizontal transformations are always the opposite of the way they appear in the equation. So 2 becomes a factor of 1/2. And similarly, the translation caused by this positive 1 will actually be a horizontal translation of -1 unit. So if I want to find the new endpoints of the domain, I will take the old x values and I will multiply by 1/2 and subtract 1. So half of -6 is -3, minus 1 is -4. Half of 4 is 2, minus 1 is 1. So here's the domain of function p. Now we need to find the range of function p. So what are the transformations that will affect the y values? These will appear outside of the function, and they operate exactly the way they look. So to find the new endpoints of the y values, I can just multiply the old y values by -3 and then add 5 to them. So -3 times 10 is 30, plus 5 is 35. -3 times 3 is -9, plus 5 is -4. So the range of p will be like this. Make sure you put these in order from least to greatest. Hey guys, don't forget to like and subscribe, but also if you found this video helpful, there's a lot more where that came from. You can click the upper link, which will take you to the whole unit playlist, or you can click the lower link, which will take you to the next video in the playlist. See you there.